move along where we're compartmentation. And these are sphincters. Now, you don't know that much, but your stomach makes acid, right? You know that much. You have stomach acid, right? Well, you don't, it belongs in the stomach. You don't want it somewhere else. Okay, so you create compartments. And these compartments are separated by what we call sphincters. We'll get into them. Some are real sphincters, like the smooth muscle that contracted, and others are functional sphincters. They're just a zone of high pressure. But basically, they regulate the movement of the red on red. They regulate the movement of time from one compartment to another, and they also regulate digestive secretion, like the sphincter of Odin. I assume that Dr. Odin came up with sphincter of Odin. Okay, that's where the pancreatic enzymes and bile come out into the urine. These are some general rule of thumbs that if you're increasing motor activity in the GI tract, you usually relax the sphincter, because if you're trying to move something, you don't want to close off, and vice versa. Okay, so parasympathetics usually with acetylcholine, there's an increased contractile activity through the enteric nervous system. Okay, then you want to open up your sphincter, so the opposite effect of the sphincter, and reverse sympathetics. Okay, now this will be the upper esophageal sphincter. We'll be covering that today, this week. But that upper, and it usually prevents air from coming into the esophagus when you're trying, ordinary. Except when you want to swallow, then it opens and allows you to swallow. The lower esophageal sphincter is important because the stomach makes acid, and that acid can go back up, keep going down. Either way, you want to control that compartment because acid is not a no-no. You don't want acid in places where it doesn't belong. The lower esophageal prevents gastroesophageal, stomach, esophageal reflux, going backwards. And then you have the pylorus, which regulates the movement of chyme from the stomach to the intestine, gastric empty. You'll get used to this terminology. Sphincter of Odin I mentioned. And then you have the Heliosecal Junction. I should have got rid of the valve. It's not really a valve. It's okay. Heliosecal Junction that regulates movement of chyme from the helium into the colon. Okay. And more importantly, we'll see that it prevents colonic contents from backing up into the helium. Okay. And then you have internal anal sphincters and external anal sphincters. Now you have control on the way in and control on the way out. For example, the upper, we'll get to this later this week, the upper esophagus, the lower upper esophageal sphincter, you have control of that. The nerves can control that. Okay, that's driving muscle in the upper part of the esophagus. You'll get that in anatomy, I'm pretty sure. And you have control over the external anal sphincter. Okay, you can control whether you defecate now or later. But everything in between, it's up to the GI tract to decide what to do. You don't know. Right now, you're processing your lunch, probably. No one's telling you what's going on. Now, we're going to be digesting material that we ingest because usually it's just too large for us to assimilate it to. We have to move this from outside the body across the single epithelial lining into the blood for delivery to other tissue, right? Whatever nutrient. Now, usually there's three major macronutrients: protein, carbohydrates, and lipid. Okay, those are the three major ones. And what I'm showing you here is the location of the enzymes involved in hydrolytic process. Every single one of these involves hydrolytic processing, okay? It's using water to break bonds, peptide bonds, saccharide bonds, or ester bonds, like acidic bonds with carbohydrate. And here I'm showing luminal location. That's going to be pancreatic enzyme. Every one of these components, whether it's protein, lipid, or sugar, are going to require pancreatic enzyme to break them down. Okay. And these pancreatic enzymes, over the pancreas here, the sphincter down there somewhere. And these enzymes are going to be responsible for 90%, if not more, 95% of all hydrolysis, okay? We'll bring up other enzymes that may play a role, but they're really minor enzymes. But the major one that initiate hydrolysis of all your ingested nutrients. And they're delivered to the small intestine to the ducts, sphincter of Oddi. Now, with proteins and carbohydrates, I will cover lipid. Once they're processed, ester bond, they're all lipid soluble and basically pass through the epithelium because they're lipid soluble, just like the membrane. But the water soluble material is still usually too large and requires enzymes that are located in the brush border or the microvilli. I don't know if you know that is already. Brush border enzyme. And these enzymes are situated such that the catalytic sites are facing outside of the body or in the lumen. Okay? So as you generate, let's say, disaccharides or something like that, then these enzymes of brush border further hydrolyzing to smaller units for absorption. Okay, and this is true of both protein or carbohydrates. Okay. And then finally, you know, it's the only ones that are involved with cytoplasmic peptidases play a role in processing some of the final protein products. Because basically you're going to be transferring from the epithelium to the blood side, you're going to be transferring amino acids. Okay? So you're going to be transporting some peptides into here and cytosolic peptidase will be offered within the cytoplasm. We'll get to that later. We'll see this again. To absorb the material, obviously, I've already mentioned it was lipid, it's hydrophobic, it's move or lipophilic, whichever term you like, they move right across the epithelium. You don't need special transport mechanisms for them. But for the water soluble solids or hydrophilic solids, you're transporting them using carriers of protein within the lipid membrane. And again, here you have the luminal side, which is outside. This will be interstitium or blood side. I wish it could do that. Anyways, and these are this is the epithelium here. Now, I think you know that sodium ATPase. You know that one, right? Can't sure cells can't live without it. That's the primary active transport system. And it serves important to because it facilitates what we call secondary active transport. It's still active transport, but it's using indirectly the energy derived from this transport system. This is primary and secondary. Let's take a look at the primary sodium ATPase moves with the 3 sodium out with 2 potassiums in, okay? So you're moving 3 positive charges out and only 2 in. So the inside of the cell becomes negative with respect to the outside. That makes sense? And that's what's shown here. Let's say this is 0 outside the body in the lumen, and this is minus 40, okay, within the cell. All right? So it's negative, right? The other thing that the sodium ATPase does is move sodium outside of the cell. Now let's forget the charge, just the concentration of sodium gets reduced inside the cell because you're pumping it out. Does that make sense? So what you're doing is you're creating an electrochemical gradient for sodium. Okay, you've had it before, right? No, yeah, a little bit. Okay, so now sodium has both the gradient, the concentration gradient, and the charge forcing it in. So all you have to do is open up or let it move, and it's going to move inside the cell. Okay. So, but the sodium movement here is coupled to other transport materials. For example, this particular transporter will move in some solids, okay? You might go talk glucose or hexose. Any glucose or galactose, for example, we'll come to that later again. But this transporter has to bind both sodium and one of these amino acids, sugar, water-soluble vitamin, get the biosol from other things, another solid, and then it moves. Okay, and sodium drives the movement. So basically, it's sodium being moved down its concentration gradient and dragging a solid with it. But this transporter won't operate unless both sodium and another solid is attached. Does that make sense? So you need that for this thing to work. And the major energy for this is coming from the sodium ATP, which creates the electrochemical gradient for sodium. Okay. We'll see this again. Water movement, called osmosis, I think, but basically it's really simple. Everything, you know that everything moves down its concentration gradient. You know that, right? From high concentration to low. Well, osmosis is the same thing. We're just talking about water concentration. Okay? Water is more concentrated when the solution is dilute. And so it's going to move to where the solute concentration is higher and the water concentration is less. Makes sense? So it's still the same thing, but it's called osmosis. And how does this work? We'll come to this. It's an interesting concept. You've got to understand it for the rest of GI. And again, here's the lumen, here's the blood side, if you will. Put in the capillary, lymphatic here. It's going to be important mostly for lipid. But anyway, you move glucose and sodium through that transporter, or it could be amino acid or something else. You're moving the solid into this paracellular space. That's where these transporters, there's one coming, the sodium glucose co-transporter, and then there's the glutes, we'll get to that later, moves it in here. So there's a solid being moved. What does that do? That's increasing the solid concentration here, so water moves. Water is always going to follow the solid. It doesn't matter what direction you're going, but if you move a solid across the membrane, water is going to want to follow, okay? Sometimes it's facilitated by pores, they're called aquaporins. We'll get to that. Aqua means water, right? Anyway, you move solids first, water follows, and then the entire thing gets moved into the interstitium, leads through capillaries or lymphatics. Okay, pretty big book. Secretion. Intestine also secretes. Then you'll see these lines again. Okay. Let's look at this again. This is CFTR, cystic fibrosis, transmembrane. They don't have the C for conductance regulator. You heard of cystic fibrosis, right? Basically, what's the genetic defect in this particular, it's a channel, primarily a chloride channel, bicarb, mostly chloride, and here other terminology, apical, basolateral, interstitial, blood. You've got to get used to the terminology. You don't have to memorize it. Apical means top, basal means the base of the cell or the basement membrane. Okay, two important things. This is a channel. Now, usually, when you have a secretory process, it's going to be chloride driven. Okay, that's why I'm showing you chloride. Okay, and, right? So what's going to happen? You need chloride so that you can move it. this one, you're going to see this particular transporter wherever you see something that requires chloride to move. What is it doing? It's electroneutral. It's moving sodium and potassium, which is two positive charges, but it's moving two chlorides. You're getting two chlorides coming in every time this pump turns over, right? So it's an advantageous for then once the chloride builds up, it just goes down this channel, okay? Now, water, wow, and what I've done here is NKCC. These are all defined in the notes. This stands for sodium, potassium, 2-chloride. It's an abbreviation. You'll see all this again. And see, the secretion is now going from the blood to the lumen. And you can, ordinarily, the GI tract is secreted. If we absorb it all, it's secreted. Okay? And the pancreas will secrete. Yeah, okay. Get rid of it. Mucus secretion. This is a goblet cell. You know what the reason it's called a goblet. I'm drawing it upside down so it matches the cartoon here. If you turn it right side up, the goblet stands for like a cup, you know, wine goblet or whatever. In the old days, they used to do that. It's a goblet shaped like a cup. Now, this is an upside down. And all these pale-looking granules of mucus. Now, the mucus is concentrated. I think you know that. Blow your nose. That's mucus. Okay? But these cells are a lot. Maybe small intestine, and in the stomach, it's a major. They're not called goblet cells in the stomach, but they secrete mucus. They're called mucus cells. And they concentrate the mucin. Now, mucin, you happy with glycoprotein? Glycoprotein. Anyway, glyco means it's going to have sugar, right? Glyco. It's a protein. It has a lot of sugar molecules. These are negatively charged, and that's shown here, negative. Now, to concentrate them into these storage granules for release, what they do is they acidify the inside of the granule, which is shown here, acid. You know, this is a symbol for acid, right? Proton. Yeah. And calcium. What does that do? You got a positive charge here. It neutralizes the negative charge and allows you to compact this material. If you didn't have this, it would look like this. These electrical charges would separate. They repel each other. Okay, that's why when you're secreting mucus will go into. This will be the lumen here. Usually, you're going to have bicarb secretion. We'll get to this again, don't worry. And what it does is it's going to neutralize the calcium and acid. Carbonic acid disassociates into water and carbon dioxide. We'll cover that again. But anyway, now they repel each other and they spread. So you get this compact mucus coming out of the cell, and then it spreads and imbibes water with water. And so it's spread like a thin film surrounding the epithelium, covering the epithelium. I think that's it. Now, the mucus layer, I call it layer because they're not static layers, they're dynamic. You have a very inherent thick mucus layer on the surface of the epithelium, and this is my cartoon of the stomach. These are villi. But anyway, you have this thick mucus, okay? You have enzyme movement, and they'll attack anything. You gotta get used to the fact that the GI tract outside of the body, and it's a chemical vat, basically. They're dumping all these enzymes, whatever. Anyway, they'll attack anything, including each other. So we'll come to that. But anyway, you get proteolytic cleavage of this mucus, and so it just gets looser and looser. Okay. What's the significance of it? This loose layer just is washed down by motor activity. When you start increasing propulsive activity or gastric empty, you're washing away this mucus layer, right? But you won't wash away the thick or firm inner layer. And what happens? It's dynamic in the sense that if you wash some mucus away, then the surface of this particular mucus here gets degraded and expand, and it kept doing that. You lose mucus, you secrete more mucus, okay? So you keep this layer moving. We'll see the significance of that later. It's really important for bacterial clearance. This is the places, much guess where you're going to have mucus and why it's important. Almost anything accessible to the outside, primarily female, but lungs, by the way, that cystic fibrosis, transmembrane regulated CFTR, people die from that. That's called cystic fibrosis, from lung problem. But there's GI problems as well. But you'll have mucus in your oral cavity, in your mouth, you'll have mucus throughout the GI tract, liver, pancreas. So it's a major player in this. Now you see, we could have just finished this the first time around. And this is I don't know where I got this from, but another review. And you don't want to memorize it, just come back and look at this. You've got a handle on the different functions of the GI tract. A different way of presenting it. They present here in terms of digestion, absorption, motility, secretion, these are major functions. A little different than we will. That's it. So if you want, I can try to use next time the handheld microphone or stick with this. But this is the only way we can record. All right. So have a good day then.